In this video, we're going to look at optimization of functions of two variables. Okay, meaning how do you find the extrema, relative extrema, the maximums and minimums? So in a function of two variables, f has a relative maximum at a point a comma b if for every point near ab, the z value f of ab is greater than or equal to all the other z values f of xy that are nearby. Okay, here's a picture right here. This has the largest z value at that maximum point. At every point nearby, the z value is lower, okay, less than or equal to that z value at the max. F of xy has a relative min at ab if for every point xy near ab, f of xy is less than or equal to f of xy. In other words, if that z value is less than all of the nearby z values. Okay, as you can see from these two pictures here, the relative extrema are going to occur where both partial derivatives equal 0, both the partial with respect to x and the partial with respect to y. If both partial derivatives equal 0, then you may have a maximum or a minimum. So let's start by just practicing finding the points where both partial derivatives are 0. So for this function, f of xy is equal to x squared plus xy plus y squared minus 5y. We're going to need to first find the partial with respect to x. So the derivative of x squared is 2x. If we're treating y as a constant, then the derivative of xy is that constant y, because it is like the coefficient of x. And the derivative of y squared and minus 5y are both 0. So that's the partial with respect to x. Next, let's find the partial with respect to y. So the derivative of x squared is 0. Y is like the coefficient of x, so the derivative of x times y is y. The derivative of y squared is 2y, and the derivative of minus 5y is minus 5. So we may have extrema where both derivatives are 0. So let's practice. We're going to set both derivatives equal to 0 and solve. This will often give you a system of equations in terms of two variables. It turns out this one, though, is not a system of equations because my partial with respect to y, it's linear. I've got y plus 2y, which can be simplified to 3y. And we can move the 5 over to get 5, so we can get y equals 5/3. And then we can simply plug that in over here for this y right here. If we had a system of equations, you would have to use solving techniques from algebra. But we can solve for what x is equal to when y is 5/3. So we get 2x equals negative 5/3. If I multiply both sides of this equation by a half, then we get x equals negative 5/6. So therefore, the point at which both partial derivatives equal 0 is negative 5/6 comma 5/3. Okay, now that point is called a critical point. And if we have a relative extremum, it will occur where both derivatives are 0. Okay, and that's called the critical point of the function. Okay, we use what's called the second derivative test to help us determine whether we have a max, a min, or something else at each critical point. The problem is that not only do maxes and mins occur where both partials are 0, so do these things called saddle points. And you can see just from the diagram, it looks kind of like a saddle. This is an example of one where along this y-axis in this direction, this surface has a maximum in that y direction, but along the x-axis, okay, it's got a minimum. So you have a max in one direction and a min in the other. So it's not really either a max or a min of the function. It's called a saddle point. So the d test, or the second derivative test, is the following, okay? A little bit complex. D is a number that you compute by plugging in your critical value into this expression right here. I'm going to circle it. So you can compute D for each critical value that a function has. And a function may have more than one critical point, in which case you would do this test for each of those critical points. So you compute the second partial with respect to x at the critical point, multiply that times the second partial with respect to y at the critical point, and then subtract the partial with respect to x comma y squared at the critical point. Okay, if you get that d is positive and the second partial with respect to x is positive, then f has a relative min. If d is positive and f(x) is negative, then f has a relative max at the critical point. Or if d is less than 0, you have a saddle point. And if d equals 0, the test fails. You've got to determine by some other method what you have at the critical value.